Hi, everyone. So today I'm going to talk about TorchRL, which is a new framework to code reinforcement learning solutions using PyTorch. So I work for the PyTorch team. I'm based in London, and my basically full-time job is to develop that framework. Okay, so if you look at the ecosystem of reinforcement learning libraries, you can basically find things that are around so libraries that are more targeted toward research or production. You also have other libraries that are a spin-off of the project. So basically scientists that were working on a certain thing and said, hey, well, look, I think that most of the solutions we have developed, we could like outsource that and do an open source repo with that. That would serve a greater purpose. You also have like laboratory initiatives, so PhD students that during the course of the PhD have kind of the same reasoning, you know, like they coded lots of stuff and they say, why not open source that on an independent repo and something that could be reused for other purposes. The problem is that most of these things are not maintained on the long term because when people start doing something else, and they usually do, they stop maintaining the library. And so that's, even though you have great stuff out there, many of these projects have ceased to be maintained after a little while. And then you have other things that have a broader scope and that have a broader support, like for instance, stable baselines or RL-lib, etc. But those things are quite different from what we try to do with TorchRL. With TorchRL, what we try to do is to have a library that is highly modular in the sense that if you want to use TorchRL, you should not be forced to use the whole thing. You know, if you just want to use one component like the replay buffer we talked about before, or just a loss function, or even just a functional, something that you find nice because it's efficient and it's easy to use, should be able to use just that thing without adopting the whole ecosystem. And the other thing that we're trying to do is to enable people to quickly experiment new ideas and not to take like big agents that you would build, you know, already that would be pre-built and that you would just say, okay, my agent.train and it trains everything for you. We don't really like that in TorchRL because we think that doing this thing does not really give you a full control over all the lower level components that are in your code. Right. So this is like sort of what we want to cover with TorchRL, and as you can imagine, it's very ambitious. Like we want that any newcomer in RL can find something, you know, in this library to say, okay, I don't know much about RL. I know a little bit, like I read a couple of papers or whatever. And when I go to the repo, I already find, you know, something that that satisfies me. You know, I can understand what's going on. But we obviously want to have like reinforcement learning researchers that are highly experimented in the field to be also satisfied by the solutions. And it's not easy, you know, to give a component that is not that trivial that anyone would say, well, you know, I could code that in 5 minutes, but also that it's not too complex such that newcomers like can find something out of it. There are other libraries, you know, some other libraries that are really targeted towards baselines. They want to reproduce existing results. That's obviously something we want to do. We want it to for you to be able to run things that already exist, but we want also to enable other people to do new algorithms, you know. And again, it's not always easy to balance those two things together. So when I started the project, I went around and I asked a bunch of people at Meta, but also outside of the company, you know, research scientists, etc. If we're building that thing, what would you like it to be? And what I heard most of the time was the sentence, we want a library and not a framework. And I think it really pins down to the first thing I was saying, you know, that people, they want something that is highly modular and not too much integrated, you know, because if you want to use just the replay buffer, because that's the only thing really that you want out of reinforcement learning, maybe, you know, like all your solutions are completely different. You're doing something like offline reinforcement learning, which can be closer to supervised learning or whatever. Maybe you just want to use one of the components we have. And so if we have a highly integrated library, that's great because it's very easy for you to train PPO on half cheetah or whatever. But it's not going to be easy to take the replay buffer out of that PPO and use it for your own problem. Also, we would like to have a syntax that is unsurprising, so to write things in a way that people quickly understand what they mean, if they're from reinforcement learning or if they're not. And we want to have an extended functionality. We want to go much more for breadth than depth. We want to cover many different things, and people, and God knows that reinforcement learning is something that is very, very heterogeneous. So the main two pillars, I'm sorry, the slide is cropped at the bottom, but the main two pillars of TorchRL are efficiency and modularity. So again, it's a tricky balance to strike, efficiency and modularity. To give you an example, there are libraries that they don't decide to use PyTorch or TensorFlow, for instance. They cover both. So that's a great example of modularity. You can choose the backend that you want. But the problem is that once you start doing that, and you want to move things from one process or one node to another, you cannot use the solutions that are provided by PyTorch or TensorFlow, or it's going to be hard. So what you're going to do is that you're going to transform things into NumPy array or something like that, and then pass it from one process to the other. And this is really time consuming. You know? So we need to make some kind of decisions to be efficient and while still being modular. And so we propose various modular solutions, and I will come into that a little bit later, but to give you just like the headline, we have fast and multiprocess data collectors, efficient distributed replay buffers, vectorized environments, etc., etc. So we have like across the library many different solutions that we want to be efficient. And regarding modularity, that's going to be like the main focus of the rest of my talk. We really want to have classes that are both usable independently, but also that talk nicely to each other. Right, so modularity. Let me make a step back and think about what reinforcement learning is compared to other domains, you know, because when I started this library, we were looking at other domain libraries like Torch Vision, Torch Text, and Torch Audio, which are really about the media. And if I take the example of Torch Vision, I would say that, well, it's a bit unfair maybe, but their life is easier than ours in reinforcement learning because they know what kind of media they're going to have. They know that it's going to be an image. And so you have a data set that delivers an image. You pass your image through a series of transforms. You get a transformed image. You pass your transformed image through a model. You get a prediction. You pass your prediction through a loss module. You get a loss value. You backpropagate that, train your model, and go back collecting another bunch of images, right? So generally, it's always the same thing, and you know that your components, they're gonna read images and nothing else. Reinforcement learning, unfortunately, it's not like that. Sometimes you have compiler stuff, and sometimes you have control, robots. Sometimes you have language models. So you have very different things, and it's hard to build one API that can swallow everything in a single way, And for instance, if you take the Gym API we talked about before, the Gym API, when you call environment.step, so it's basically when the environment receives an action and outputs a new observation. When you call that thing, sometimes you will get an NumPy array, sometimes you will get a dictionary, sometimes you will get a tuple. So you cannot really know in advance because it's so much dependent of the problem you're looking at that you cannot really know what's going on. And so we try to abstract that thing, and I'm going to show later the solution that we found for that. Another thing is in reinforcement learning, sometimes in supervised learning, you have like training mode and evaluation mode. So evaluation is basically everything about inference, and training is just like when you train your model. In reinforcement learning, we have a whole bunch of other levels of duality of how you execute your model, because you also have exploration versus exploitation. You have the loss computation, the moment where you compute your loss and the moment where you collect data. And all of these things, sometimes you're exploring in one and not in the other, and sometimes you're in evaluation in one and not in the other, etc. So it's not always easy, to basically put all of these things together in all the combinations that you can imagine. Okay. So this is a rather loaded slide, but it's basically about the solution that we found for TorchRL to handle the problem of the multiplicity of the input-output types that we have. And the solution that we came up with is called TensorDict. So basically, TensorDict is a new primitive for PyTorch, really dedicated to PyTorch. And the thing that TensorDict does is that it carries any number of tensors that share a common batch size. So it's basically the leading dimensions of your tensors. So it's sort of saying, okay, I have an observation, an action at time t, an observation, an action at time t plus 1. I have a reward, a done state, etc. All of these things, I put them together in a dictionary or potentially a nested dictionary. And so you get that thing, you get that structure, and now you have all that is well packaged together, and you can move that from one process to the other because TensorDict supports distributed computation very efficiently. You can move that from one device to the other. You can execute operations on all the tensors, etc., etc. So now we have that one thing, and everything is named inside. So you can really keep track of everything that's going on inside the TensorDict. And now that you have abstracted the input and output of all the classes in TorchRL, we know that all the classes, they're going to read a TensorDict and they're going to write a TensorDict. And that basically allows us to put everything together in a very nice way because our replay buffer now, we know that it's going to read a TensorDict and write a TensorDict. So we don't have to customize the replay buffer saying, oh, well, wait a minute, if it's a tuple, you do that. And if it's a dictionary, you do this, etc., etc. Using TensorDict, we can just say, okay, it's always going to be a TensorDict. Its structure is the structure that you want. We don't put any constraint on that, but the only thing is that it's sort of the dictionary that has extra features from Tensor. All right. Yeah, I just have 5 minutes left. So now I'm going to show you how with TensorDict we can basically code an algorithm with TorchRL. So this is a figure from the paper we recently put on archive. So on the left side, you see a figure of a typical training loop in TorchRL. And the big arrows are basically every time you pass a TensorDict from one component to the other. And I should emphasize that TensorDict is really the one and only thing that usually you will have to adopt if you start using TorchRL. So if you're happy with using TensorDict, you can use just a loss module independently from the rest of the library. You can use a replay buffer independently from the rest of the library, etc. It's really the only thing that we ask you to say, okay, I'm going to use that, and it's going to make your life easier, hopefully. Right. So what you see on this figure is that we have, like we talked before, we have an actor or an agent, and this agent writes an action in the TensorDict, passes that TensorDict to the environment executes that action, writes a new reward, a new done state, and a new observation into the TensorDict, and then what this TensorDict goes back to the agent, and the loop is closed. So that's basically our inference loop. And every time we get a new TensorDict, then we put that in the replay buffer that is below the blue and yellow thing. And this replay buffer basically stacks all those TensorDicts contiguously in memory, which makes indexing very, very efficient. Again, it's super easy to use and doesn't require much like knowledge or anything. And then you can sample things from this replay buffer and pass them to a loss module. Again, you take a bunch of TensorDicts, you pass them to the loss module. The loss module returns a scalar, and then you can backpropagate through the scalar and train your parameters. And this is an example of how you would code PPO in TorchRL. So it's a very, as you can see, this is the full training script. It really contrasts if you go to other libraries like stable baselines. Stable baselines, they will show that have like the same script is in 4 lines. I think it's great that it's in 4 lines, but in 4 lines you don't have much control about what's going on. In this script, it's not in 4 lines, it's much more than that, probably like, I don't know, 40, but you have a real fine control over the network that you're using and the problem that you're trying to solve, etc., etc. So you can really put every detail as you want it, and still, things are there for you, properly coded, properly documented, and properly tested. All right. So now for the next 2 minutes, I will go through the various primitives that we have. So we have various environment wrappers. You already heard about Gym, but there are many others like DeepMind Control and other things. So basically, we try to have the same API for all the environments, such that you don't have to care really about, oh, well, if I need to test, the reviewer to ask me to test also on DeepMind Control, I did on the Gym, how can I do that? It's very easy, to swap from one to the other. We have transforms such that you can transform images and other things on device after you have collected data from your environment. We have various modules that are used in reinforcement learning. We have efficient data collectors on a single node or multiple nodes, such that you can collect data if the environment, if the inference is very computationally heavy, you can distribute that across multiple nodes. Yeah, we have, as I've said, replay buffer, various objectives. So basically loss modules for PPO, SAC, and many other things. We have a trainer if you want to code things easily for you. And yeah, various loggers and utilities, etc. And yeah, that's it. So basically you can check the two repos because yeah, there are two repos. There is TorchRL, which is on GitHub, but under the PyTorch username. And also there is TensorDict, which is an independent repo because we thought that TensorDict was actually a solution that might be used by other people outside of reinforcement learning, even for self-supervised learning, supervised learning, or unsupervised learning. I don't think it's really limited to RL. It's a greater purpose library. Okay. Yeah, so I'm out of time, but there's a break now, so feel free to come to me during the break if you have any questions. Thank you.